So question 45 is about Faraday's law of induction, and it wants us to explain why if we used a stronger magnet at the same speed we would get a larger EMF. Induced EMF is equal to the rate of change of flux linkage. So even though we're keeping the speed the same, so the time is the same, what we're changing with a stronger magnet is changing the flux. So the stronger magnet would have a larger flux. That's the first point we need to make. This would increase the flux linkage. We can also say this would increase the rate of change of flux linkage, and induced EMF is proportional to the rate of change of flux linkage. So essentially it wants us to explain that we understand Faraday's law and then state how the increased magnetic field strength would affect this. Part B is about a straight conductor moving through a field. As the straight conductor moves through the field, it passes through this area that I'm shading here. Now in a time delta t, this moves a distance equals v delta t, and that's this distance here. Yeah. So the area here is just the length times this distance, which is length times velocity times delta t. And we can say area equals that. The induced EMF is the rate of change of flux linkage, so EMF is equal to delta phi by delta t. That's equal to, the change in linkage is BA, and that is obviously divided by delta t. Now we are going to use the expression we've just derived, so this becomes B L V delta t, because that's our expression for A, divided by delta t. Our delta t's cancel, and we get EMF is equal to B L V, as we were asked to prove, QED. In part C, it's building on the idea of part B. It's about a rotating copper disc with a contact here at P and a contact here at Q. We can consider, though, the copper in between P and Q to be a straight conductor moving with an average velocity of the midpoint there. And we've just shown that the induced EMF is BLV. We'll use that later. Initially it asks us to calculate the angular speed of the disc, so it's a circular motion question. It tells us the radius of the disc is 34 millimeters and there's 16 revolutions per second. This is the information we need here. So angular speed omega is equal to 2 pi f. 16 revolutions per second means that f is 16. So 2 pi times 16 is equal to 100.5 radians per second. The midpoint of the radius of the disc is at a distance of 32 millimeters because the radius of the disc is 64 millimeters. So we're going to use the formula for linear speed v equals omega r. Omega, which is calculated as 100.5, and the radius is at the point at the midpoint, which is 32 millimeters. So the midpoint of the disc is moving at 3.22 meters per second. For part 3, it says hence or otherwise calculate the EMF induced across P and Q. On the previous slide I said that we could consider the line between P and Q as a straight conductor moving at the average linear speed of its midpoint, which we've just calculated as 3.22 meters per second. So it wants us just to use EMF is equal to B LV. In this case it tells us the magnetic flux density is 28 milliteslas, and the length of the conductor is 64 millimeters. That's the radius of the disc. So 64 times 10 to the minus 3 times the velocity, or the average velocity of it, which is 3.22 meters per second. And that gives us an induced EMF of 5.8 millivolts